So I'm going to give a more technical talk than we've heard so far. Hope that's okay. But it includes some joint work with Jack. No good deed goes unpunished. I'll expose some old bugs in the BLAS and LAPACK that have been there for a very long time and what we're going to do to try to fix them. But the first topic is going to be some new communication avoiding algorithms. So so I will preach to the choir and spend a minute telling you what's communication and why we want to avoid it, and give you a few examples of past algorithms where this has been successful, and then tell you about two new ones. One of them is matrix multiply and mixed precision. That's a pretty straightforward extension, and you can actually go faster than matrix multiply, than GEM if you take advantage of the mixed precision. And it turns out the same trick works for multiplying a dense times a random matrix. And we're actually close to beating GEM, beating MKL. So then I'll go on to fixing old bugs in the BLAS and LAPACK and making them resilient to exceptions. I'll show you some motivation for why we should care about this more than we have in the past, and a tentative plan to fix these problems. So next slide, please. So what is communication? Well, as everybody here probably knows, the cost of running an algorithm, you count the number of flops, you count the number of words moved, you count the number of messages in which you package all the words and send them from one processor to another or between main memory and cache. And then you multiply them by 3 hardware parameters: the time per flop, the time per word or the reciprocal bandwidth, and the latency. And all of these 3 hardware quantities, the time per flop and the reciprocal bandwidth and the latency, are improving over time. Despite the death of Moore's law, things are changing a bit, but time per flop is much, much smaller. And so the picture below is taken from data in Patterson and Hennessy's latest textbook. And all of these curves on a log scale show you how much all of these quantities, alpha, beta, and gamma, have improved over time. Not quite straight lines on a log curve, but the time to do a flop is at the very bottom, the dark blue, and all the other curves are going down too, but not quite as fast. And so it's the same story for saving energy. And so next slide. And so here's just a little bit of history of what many people have done, not just us, to take advantage of this to come up with new algorithms. There's sort of 3 different approaches that people have taken. One is you do the same operations just in a different order. And that has been used to speed up dense matrix multiply and sparse dense matrix multiply by factors of 12 and 100 and so forth. Graph theory, all pairs shortest path, and in body codes. Then, of course, you want to sometimes have a different algorithm, but still get the same answer, modulo round off. And there have been a lot of algorithms that have been invented by various people too, including tall, skinny QR, improved symmetric eigensolvers, improved iterative methods by CG-STAB, and you can't avoid machine learning these days, of course, so coordinate descent lasso have also sped up by large factors. And finally, if all you care about is roughly predicting the same dogs and cats, you have a lot of choices in machine learning, and you can use a completely different algorithm and get a different approximate answer. And there, much more is possible. So for support vector machines, there's been big speed ups. And for ImageNet training, the biggest speed up you'll see here on this page is 135x. And so this work has been recognized in a number of ways. And sorry, the animations don't work. When I was teaching the new matrix multiply algorithm in my parallel computing class a few years ago, a student thought it was a good idea and formed a startup called Nirvana, which was acquired by Intel a few years ago. And then Torsten Hoffler, and completely independent work, won a Best Student Paper Prize at SC19 for improving that algorithm, even by a constant factor more, and actually making the upper bound and the lower bound match on the communication. TSQR won a prize, but that work hasn't stopped. In fact, just a week ago, we released a new version of it in the latest LAPACK release, which includes reconstructing householder. The support vector machines won a prize, and the work that got 135x speed up was actually adopted into the industry standard machine learning benchmark. So now it's used whenever anybody tests their algorithm and see how fast they can train dogs and cats. Okay, next slide. So now the new stuff. So let's suppose we want to do mixed precision matrix multiply. So this is a placeholder for many other mixed precision algorithms that people here are interested in. So I want to multiply A times B, where B and C are both occupy 1 word each, but A is lower precision. So I'm going to use rho as the parameter to indicate what its precision is. So maybe rho is a half if it's half precision. And so what we want to do is get a new lower bound that's lower than before and an algorithm that attains it. And it's a pretty simple change to the existing analysis. We're still going to use the Loomis-Whitney inequality, which says that if I have a certain number of entries of A, B, and C, sharp A, sharp B, and sharp C, how much work can I do? And it's the same formula as before. And so what I want to do now is optimize that quantity, given that I can have a certain amount of data available in a segment, which is what I break up my sequence of instructions in the code to do. And I can prove that the number of words moved is smaller than it was before by a factor of rho to the 1/2. So for example, if my matrix A is half precision, I can improve the previous lower bound by a factor of the square root of 1/2. And is there an optimal tiling? Yeah, it's quite straightforward. We're just going to have rectangles now instead of squares. So A, the low precision matrix, is going to be larger, by a total factor of rho, and B and C are going to be rectangles. And that is the optimal tiling that attains it. So let's try now the same idea for randomized linear algebra. And so there, what is the kernel that we all want to, that many people want to do? You want to take your input matrix and multiply it by a random dense matrix, full of Gaussians or random plus minus ones. And so now we're going to use the same trick. Suppose that each entry of your random matrix A, and it's cheaper to recompute that random number than it is to fetch it out of memory. So how much better can you go? And it's pretty much the same analysis that you get these rectangular tiles in theory that says what's the best way to do it. And the shape is going to depend on the cost of your random numbers. So for example, random plus minus ones, those are Rademachers, they're going to be cheaper than Gaussians. So let's show you some preliminary results, performance results in the next slide. And so this is work by my student Vivek Bharadwaj from about 4 p.m. yesterday. So this is pretty recent work. And so the vertical axis is the fraction of peak. Horizontal axis is the tiling shape, which is all very rectangular. And the green dotted line is MKL. So that's going to be, ideally we would surpass that. And there's a hint that we can. So the blue line is a homegrown version of GEM that is based on a microkernel that Vivek wrote himself based on a reference at the bottom of the page that's tuned for this Knight's Landing processor. But the advantage of this kernel is that all the parameters are exposed so we can change the tilings and so forth. And so MKL gets 79% of peak, and the homegrown version gets about 77% of peaks, so it's doing a decent fraction of that. So that's going to be our starting point because we obviously don't have the source code for MKL. So if we try doing an expensive random number, we get the red curve at the bottom. So we can't do better than GEM. If we use a cheaper random number or a pseudo random number, just consecutive integers, we get the yellow curve. But if we do something very, very cheap, and this is just sort of a test case, and we use constants for the random number, we get the green curve. So we're actually beating the GEM, our homegrown GEM. And if we don't count the cost of, if we assume that generating random numbers is completely free, we get the red curve, and that actually beats GEM. So the fact that the green curve beats the blue curve means that you can beat GEM because that's an apples to apples comparison. And so what we're hoping to do, and as time goes forward, is we have a lot of collaborators who want to build hardware accelerators to generate random numbers faster. So that can make the random number generation arbitrarily cheap. In that case, we do have a possibility of beating GEM. Okay, so that is the end of the first part of the talk. The next part is fixing old bugs in the BLAS and LAPACK that have been there for a long time. No good deed goes unpunished, so we have to keep fixing things. And we've known about exception handling for a long time. It's all rules for it are in the IEEE standard, but people don't always pay attention. And there's some famous examples like the crash of the Ariane 5 rocket and a naval propulsion failure. But this is a post from, from last November, I believe, on Reddit. And this was a crash in a robotic car race. So the car was going around a curve, and suddenly it takes a left turn, a right turn, and it crashes into the border. And there was a Reddit post by the engineer in charge of building it saying it was a NAN. So obviously, as the world becomes more automated and there are more cyber physical systems that we depend on, whether it's our self-driving cars or our heart pacemakers, whatever, we got to care about exception handling. No, next slide. So let me give you some examples of bugs that have been in the BLAS for a very, very long time. And the first one is Isomax, the simplest possible BLAS1 routine you could imagine. It just returns the index of the largest entry of the largest absolute value. Well, let's suppose we run Isomax on an array of length 3 and the inputs are 0, NaN, and 2. It tells you 2 is the largest. But if I permute that and put the NaN first, it tells you the NaN is the largest. So that's simply because NaNs do not propagate consistently, because obviously the BLAS were written before the IEEE standard. And so that is a bug. And Isomax, the complex version, is even worse. If you put in a finite number that's close to overflow as the first entry and an infinity in the second entry, it'll tell you the finite number is the largest, not the infinite entry. So this is one example of a bug. Next slide. So here's another sort of a bug in Rank1 Updates. And the bug here is that the Rank1 update checks for zeros in the vector y. And if there's a 0, it doesn't multiply by it. And so that means that there's not going to be, if there's a NaN or an infinity in the x, that's not going to propagate in that particular location. And the same thing happens in SYR, it's symmetric Rank1 update, but it only does the checking in the X transpose. It doesn't check for zeros in X. So depending on whether you're updating the upper triangle or the lower triangle, you might get a mathematically different answer. So next slide. So the same thing happens in triangular solve. So, and that's because it checks sort of inconsistently for whether there's zeros in the solution and doesn't propagate NaN. So here's a little 3x3 triangular system to solve with a NaN in it. And it yields the answer 1, 0, 1. So the NaN does not propagate, because when it computes the 0 in the X and says, oh, I don't have to update by that. So it doesn't bother multiplying the 0 by the NaN. On the other hand, if you solve the mathematically identical triangular system, which is you transpose the matrix and then ask TRSV to solve the transpose, it doesn't check for zeros. So the NaN does propagate. And so I'm going to leave this as a little problem for the readers. You can come up, you can take all, no, back up, sorry. You can take all of these bugs and come up with a little matrix where SGESV, the linear solver in LAPACK, gives the wrong answer. All these bugs can collaborate to not propagate a NaN from that's inside the matrix to the output. So these are things we have to fix. Next slide. And so we have a detailed plan under construction to identify and fix these bugs. And we're going to, among other things, automatically check for infin-NaN inputs on most drivers. This is something that's done in LAPACK, and MATLAB is doing this already too. And we would like to provide wrappers to allow more extensive checks for NaNs and so forth. So we'll see, we're devising the plan. So there've been many collaborators working on this. Jack is obviously a collaborator, happy birthday. And if you want to actually watch the car crash, there's a Twitter post to a video, a link to a video. So thank you very much. And looking forward no, sorry, that's just an extra slide. All done. So that's the answer to the little puzzle.
Oh, thanks very much.
Yes, looking forward to continued working with you as I have for so many years. It's been a great collaboration, and look forward to fun.
Absolutely, yes.
Thanks very much, Jim. Can I just kick off with the questions? So regarding the start of the talk and the mixed precision, I think you had the data as being stored, some of the data being stored in lower precision.
Yes.
What precision are the computations being done in?
So we're doing double equals double times single. And so in that particular model, it would be accumulated in double. You could also ask, how should you best tile double equals single times single? In which case you would, the answer would also probably be accumulated in double. So tensor cores do that kind of thing, where they compute single equals, half times half.
Okay.
So all of those can be taken into account by the model. Yeah.
Yeah, and the case of a random matrix, what sort of application are you thinking of there?
Oh, this is randomized linear algebra.
Yeah.
And so the standard approach is you first sketch your matrix. And there's a lot of ways to do that. And one of the most common ones that's used in randomized SVD, for example, is you take your input matrix and multiply it by a much smaller rectangular Gaussian matrix. And then you do regular dense linear algebra algorithms on the smaller sketched matrix. And we have a project right now with Jack to put all this stuff into the next version of LAPACK.
Okay, thank you.
May I
please,
ask a question?
Go ahead.
Hi, Jim. In low precision, how random is a random number?
Oh, so that's part of the big design space, because you could have random plus minus ones, in which case, that's one bit.
But Gaussians, or what Gaussian?
Right. So that is a big question. And there's you could imagine, I think that all the data that I've seen indicates that the behavior of the ultimate algorithm, the randomized SVD or the least squares solver, is pretty insensitive to how good your random numbers are. And so you can get away with very little precision. And that's why we want to experiment with random plus minus ones and have that as an option, in our new randomized BLAS, as well as something more expensive like Gaussians. And this is also coming up because we're talking to, we have our hardware collaborators who want to build special hardware to generate these random numbers, and they want to know how precise they have to be. And so it's an interesting design space that touches many levels of the stack.
Okay. And Jim, another question about the second part of the talk. What about GPUs, which maybe don't always fully implement the IEEE standard? And how do they fare in terms of exception handling?
So many years ago, I wrote a paper with my former student Vasily Volkov, where we were trying to get, let's see, it was a bisection algorithm for the symmetric eigenvalue problem to run on the NVIDIA GPUs of the day. And it turns out that 1/-0 was plus infinity. And that caused a bug. And so we had to fix it by doing a pre-processing of the symmetric tridiagonal matrix by adding +0 to all the diagonal entries, which is a no-op in almost every case, except to change the -0s to +0s if there were any. And then we could prove the algorithm was correct. In the meantime, NVIDIA has gotten it right. That was a temporary bug. And so they're definitely trying to improve on these things. But we do have an IEEE standard, and when we design code, we're hoping that they will do the right thing and implement these corner cases correctly. I should say that even though we just came out with a new IEEE standard, a group of people have gotten together and have applied to the IEEE for a new standard already. They don't want to wait. They want to have a new floating point standard for machine learning and deal with all the low precision stuff in there. And so who knows what, we're going to be back to the Wild West that Belleville fixed a long time ago, I think.
Right. There is a question in the chat from Eric Strohmeyer. Eric, it might be better if I let you just pose the question verbally. Do you want to unmute and ask Jim your question?
Well, hello, everybody. Thank you. So, Jim, how did you, pointing out some errors in some codes to check, how did you get around having to fix them on the spot?
Well, I mean, if a bug has been in Isomax since 1979, that's why, is it a bug? That's why I put it in quotes. And so, yes, we can design algorithms that, give you something you don't expect, but it's only these, recently that people have become concerned about this level of reliability, car crashes and whatnot. So, most of the time when, if you input a matrix with an infinity or an n in it, nobody made any promises anyway. So that's why, it wasn't considered a bug, because there wasn't a promise made as to how it should behave. And so now we're trying to come up with the rules, which I'm defining as consistent exception handling. And we have a working document that Jack and I and many others have just finished that we're sharing with the community, or will shortly, to get input on whether our definition of consistency, is acceptable.
Okay, any more questions for Jim or comments?
Oh, I had one Wilkinson story I wanted to share,
Yeah.
since his name has come up many times. So
Mhm.
he came to visit when I was a grad student, visiting Belleville and Beresford. And I remember being in Evans Hall outside Belleville's office, and Wilkinson walked down the hall. And he came up to me and he said, I don't think you're nearly as smart as your advisor thinks you are. I took that mostly positively. So anyway, that was Jim Wilkinson.
Okay, well, thank you very much, Jim.